The Doppler effect is a familiar phenomena to all of us. When something approaches us, the apparent frequency of the sound is higher than the actual frequency, and as the object moves away from us, the apparent frequency that we hear is lower. Let's take a look at the reasons behind this. This picture shows a sound source, the purple dot in the middle, moving to the right. The black circles represent the wave compressions in the sound wave. The object is moving to the right with a velocity of u suffix s for the speed of the source. And we can see that the wave speed in the medium, which is probably air, is actually faster than the speed of the source because the waves are advancing to the right. And let's call the speed of the waves in the air v. Now in a time t, the period of the wave fronts move forwards by a distance of one wavelength. But in that same period of time, the source itself actually advances forwards, given by a distance speed of the source multiplied by the time period. So the source moves forwards by this distance in the same period of time. The actual wavelength of the sound is lambda, but to the observer who is listening to the sound advancing, the apparent wavelength is going to be shorter by the distance moved by the source. So the apparent wavelength is going to be lambda minus UST. Because the period is the reciprocal of the frequency, we could also write this as lambda minus US over the frequency of the source. So how does this actually affect the frequency of the sound that we hear? Well, we have this general equation for the frequency of the sound, and if we put into this equation the apparent wavelength, the shortened wavelength in here, then we're going to start building up an equation for the apparent frequency. So let's call the apparent frequency f prime. It's going to equal v, the speed of the sound in the air, divided by the apparent wavelength, which is lambda, the true wavelength, minus the speed of the source over the actual frequency. And one final step will take us to this equation. The apparent frequency equals the actual frequency multiplied by the speed of the wave in the medium divided by the speed of the wave minus the speed of the source. So this equation will allow us to calculate the apparent frequency of the sound if we know the true frequency, the speed of the wave in the medium, and the speed of the source. So for the situation where we have the sound source approaching the observer, we have the equation which we just derived. For the situation where the sound source is moving away from the observer, we have a very similar equation, but in this case the wavelength is stretched. The wavelength is not shortened by this small amount of distance moved by the source, but it's extended by the small amount of distance moved by the source. So the equation is very similar. Apparent frequency is equal to actual frequency multiplied by the speed of the wave divided by the speed of the wave plus the speed of the source. So let's take a look at an example. So here's a car approaching a person, and let's say that the speed of sound in air is around 340 meters per second, and let's say the car is moving at approximately 30 meters per second, which is quite fast. We can now use these values to calculate the apparent frequency of a sound emitted by the car's horn telling the person to get out of the way. So let's imagine that frequency, the actual frequency of the sound emitted, the frequency that the driver will hear, is 440 Hertz. So the equation we want to use is f prime equals f v over v minus us, because the sound source is approaching the observer. Let's put those numbers in there. So we've got 440, the actual frequency of the sound, 340 is the speed of the sound, over 340 minus the speed of the source, which is 30. So that's 340 divided by 310 multiplied by 440, which rounds up to 483 Hertz. So the apparent frequency of the sound that the person hears, 483 Hertz, significantly higher than the actual frequency of the sound emitted. In the same example, as the car passes, the person will hear a lower frequency. So the car is moving away in this direction and the person will hear the lower frequency. So we can calculate that frequency. F prime is equal to f v over v plus us. So let's put those numbers in. So we've got 440, the original frequency, over 340 over 340, and this time plus the speed of the vehicle, which was 30 meters per second. So plugging those numbers in, this time we get just over 404 Hertz, so a low frequency of sound is heard. If the source isn't actually moving but the observer is moving, as in this diagram here, you can see that the observer is running towards the source, we're going to get a similar effect. As the person runs along, they pass the wavefronts of sound more rapidly than they would if they were standing still. So again, if the person is running towards the sound source, they perceive a higher frequency. If they're running away from the sound source, they perceive a lower frequency. The equation that allows us to calculate the apparent frequency heard by the person is again very similar to the first equation. The frequency, the apparent frequency, is now given by the true frequency of sound, and the equation is flipped: v plus uo, so that's the speed of the observer, the running observer, over v, which is still the speed of the sound waves in air. If the person is running away from the sound source, then the equation becomes apparent frequency equals true frequency, speed of the wave minus the speed of the observer over the speed of the wave. So summarizing those two situations, when we have a moving sound source, we use this equation. The apparent frequency is equal to the actual frequency multiplied by the speed of the sound wave divided by the speed of the sound wave plus or minus, depending on the situation, the speed of the source. For the situation where the sound source is not moving but the observer is moving, we use this equation. Apparent frequency is equal to actual frequency multiplied by speed of the sound plus or minus the speed of the observer divided by the speed of sound. So in the first equation we use a negative sign when the sound source is approaching us, giving rise to a higher frequency. When the sound source is moving away, we use the positive sign, giving rise to a lower frequency. In the second equation, when the person is running towards the sound source, we use a positive sign, again giving rise to a higher frequency. And when the person is running away from the sound source, we use a negative sign, giving rise to a lower apparent frequency. So here's a couple of examples of how the Doppler effect is used in real life. Ultrasound is used commonly to view unborn child in the uterus, but it's also used to actually measure the blood flow in the umbilical cord to make sure everything is okay with the child. You can see in this diagram here we've got the picture of the the fetus. But here we've got a graph, and this graph shows the speed of the blood as measured using the Doppler effect in the umbilical cord. This second example shows a police officer with a speed gun measuring the speed of an oncoming car. In this example, sound waves aren't used, they're electromagnetic waves, and we have a modified equation that we can use to measure the change in frequency detected by the speed gun. So the equation looks like this. We have the change in frequency measured by the speed gun is equal to the ratio of the speed of the object divided by the speed of sound multiplied by the actual frequency emitted by the radar gun. So let's look at an example of how we can use that equation. Let's imagine this ray gun here, this radar gun, is attempting to measure the speed of this vehicle which is approaching. The radar gun uses microwaves of wavelength 3.1 centimeters, and using the equation v equals f lambda we can calculate the frequency to be 9.7 times 10 to the 9 hertz. In this equation, v is the speed of light, the wavelength is 3.1 centimeters. If we convert that into meters, and we get this frequency here. So we have the equation, change in frequency is equal to v, the speed of the car, over c, the speed of the microwaves, which is 3 times 10 to the 8, multiplied by the frequency of the microwaves. Let's rearrange that equation. So we have v, which is what we want, is equal to delta f, the change in frequency, over f, the actual frequency, multiplied by the speed of the microwaves. So let's say that the change in frequency measured by the radar gun is equal to 970 hertz. Let's plug all those things into the equation we've got there. So we have v equals 970 divided by 9.7 times 10 to the 9 multiplied by the speed of light. I'll just write down c because I can't fit it in, but that's 3 times 10 to the 8. Plugging all those numbers in, we get a speed of 30 meters per second, which, depending on the situation, may or may not be breaking the speed limit. So in summary, the Doppler effect is a wave phenomenon that's easily observed with sound. We hear it on a regular basis. We can also observe the Doppler effect with other kinds of waves, for example electromagnetic waves. There are 3 equations, important equations. For the moving source, we have f prime, the observed frequency, equals frequency multiplied by the speed of the wave divided by the speed of the wave plus or minus the speed of the source. For the moving observer, we have the apparent frequency equals the actual frequency multiplied by the speed of the wave plus or minus the speed of the observer divided by the speed of the wave. And for electromagnetic waves, where the speed of the object is much less than the speed of the electromagnetic waves, we have the change in frequency is equal to the speed of the object divided by the speed of the electromagnetic waves multiplied by the frequency.